In our last unit, we're going to be going over reaction rates and equilibrium. This video, we're going to focus on reaction rate factors of how to slow up or speed down a reaction and look at how energy changes over the course of a reaction. So whenever we're looking at reaction, all of it is based off of collision theory. So our rate of the reaction is the measure of the speed of any change that occurs within an interval of time. So in terms of reactions, we're looking at the rate of product formation over the course of time. Um, and all of this has to deal with collision theory, and it's based off of the numbers of collisions that are occurring. So atoms, ions, and molecules can all react to form products, but in order to do so, they have to collide with one another, and they have to have enough kinetic energy to make it an effective collisions. So if the particles don't have enough energy whenever they collide, nothing happens. They're simply going to bounce off one another. So anytime we're looking at rates of reaction, we're looking at, are there more collisions? Are there less collisions? Do the collisions have more energy or less energy whenever we're trying to figure out if it will speed up or slow down the reaction? So looking at our energy changes in a reaction first. Whenever we're looking at the collisions need to have an activation energy. This is the minimum energy that colliding particles must have in order to react. If they do not have this activation energy, they will simply bounce off one another and no reaction can occur. Two particles that have this activation energy, whenever they collide, they can form our activated complex. The activated complex is kind of like a hybrid molecule where all of the atoms kind of momentarily mush together at the activation energy barrier, and then they can either rearrange to form new products or they will separate back out into the original reactants. So depending on how they collide, how they're oriented towards one another, will determine if they're going to make new products or simply separate back out again. It's kind of a 50-50 shot. And both possibilities are equally likely. So sometimes this activated complex is also called our transition state because it's going to be transitioning from reactants to products if everything's working as it should. So looking at energy and reaction, you're going to see these potential energy diagrams. And here I've given you two samples of them. But if you'll notice, they start with a flat line on both of them. That is going to be our reactants. There's a hump in the middle, and then they end with a flat line, which is going to be our products. So we already talked about activation energy, which was the energy that the particles needed to form that activated complex. Activation energy is going to be from the reactants up to the activated complex. So here the activated complex is going to be, excuse me, I'm trying to write, at this little top peak right here will be our activated complex. I'll do AC for short. And if you look at the difference between our reactants and that activated complex, that is our activation energy. So if we actually had a scale, we could subtract these amounts and figure out how much energy would be required. Something else you can notice on here, down here is this delta H. Excuse me, it's not writing. So if you remember from thermochemistry, we did delta H, or heat of a reaction. That can also be found on these potential energy diagrams. So here our products have less energy than our reactants. So if you notice that delta H goes down, so this is a negative delta H value. So this would be an exothermic reaction because the products have less heat than the reactants. It lost energy. Um, and you can actually, yet again, if you're given a scale, you can subtract and find these values. So remember that activated complex is going to be at the top peak. To find activation energy, or EA, sometimes you'll see it written, you're going to do the difference between the activated complex and the reactants. To find delta H, we're going to do the products minus the reactants. That will tell you if it's going to be a positive delta H or negative delta H. We can note those same things on the diagram on the right. We start with our reactants. We have the hump going up to the activated complex and then becoming products. Our activation energy that we had highlighted in yellow is the difference from the reactants up to the activation energy. So they drew it off to the side instead of underneath the curve, but it's still the same difference. They also noted our heat of reaction, the difference between the products and reactants. And here, the products have more energy than our reactants, so this should be a positive delta H value, meaning this is representing an endothermic reaction that is absorbing heat. As part of your practice, you'll have one of these to actually go through and label the reactants, products, things like that, and it will give you a scale so that you can actually find the value for activation energy by subtracting the activated complex and reactants, and you'll be able to find the delta H value by subtracting the amount for the products and reactants. So we're going to look at factors affecting reaction rates. Remember, we said this is all based on how many collisions there are and if the collisions have more energy or less energy. One thing that is going to affect reaction rates is temperature. In general, raising the temperature will speed up the reaction, and lowering the temperature will slow down a reaction. If you remember, temperature was the kinetic energy of particles. So if you increase the temperature, the particles have more kinetic energy, they're moving faster, therefore there will be more collisions between the particles, and it will end up producing more products. So anything that's going to create more collisions should create more products. But this one, the energy of the particles increases, meaning the speed increases, there's more collisions, more products. In terms of concentration, remember concentration was looking at how much is dissolved in a substance. If you increase the number of particles in a certain volume, more particles simply means there's not a lot of empty space between the particles. They're going to collide more often. So this would end up increasing the reaction rate. I like using analogies, you guys know. So imagine that we were in school and it's during class change. There's so many students, it's hard not to collide and bump into people on a daily basis. In terms of temperature, this would be, low temperature, you would simply be walking to class, whereas a high temperature, you would be running to class. If you're running to class, it's more likely that you're going to collide with others around you versus if you're simply walking to class. In terms of concentration, this would be like being in the hallways at class change versus going to the restroom in the middle of class. if you're going to the restroom in the middle of class, there's not a lot of traffic in the hallways. So it's not as likely that you're going to collide with other students in the hallway. Whereas if it's class change, everybody's in the hallway. So there's simply more people, so you're going to end up bumping into more people and it's going to have more collisions. Other factors affecting reaction rate, the first one we're going to look at is particle size. The smaller a particle is, it has a greater surface area, so there's more locations for collisions to occur. So it's going to end up being a faster reaction rate. So increasing the surface area increases the number of collisions, which speeds up the reaction. We also mentioned this in our solutions. Whenever we were talking about dissolving sugar, it's going to be easier to dissolve little grains of sugar versus a sugar cube, because each little grain of sugar is able to dissolve, whereas a sugar cube, only the outside particles can dissolve. Those inner particles are going to be untouched. We can also use a catalyst to affect our reaction rate. We talked about catalysts with reactions, but we just mentioned that they speed up the reaction and they're not used up, but we didn't actually talk about how catalysts react. So catalysts are substances that increase the rate of reaction without being used up during the reaction. And how they function is they actually lower that activation energy needed for the reaction to occur. So if the particles don't need as much energy to make products, they will therefore make products faster. And remember, catalysts tend to be written above the yield arrow in an equation. On the following slides, so here I have some pictures of catalysts. So you may have seen a catalyst like this in biology, where it took two substrates together and combined them to form a new substance. Here we also have included an inhibitor. An inhibitor is a substance that interferes with the action of a catalyst. So it actually blocks one of the sites of a catalyst so that the catalyst cannot bring those substrates together. It cannot do its job. In terms of our potential energy curves, here in red you'll see the uncatalyzed reaction. Whenever there's a catalyst, it simply does not need as much energy in order to change into products. Note that the delta H was unchanged, the reactants and the products were unchanged. The only thing that changed was the energy of that activated complex, therefore the activation energy was also changed. You can also look at pressure and volume as reaction rate factors. Noting that anytime it's going to force those particles closer together and there are more collisions, it will speed up the reaction. So a smaller volume is going to force more collisions to occur. Also, a higher pressure will force more collisions to occur. I want you to look at the reaction rate factors and potential energy diagram practice and complete this over the next few days.